at that slide. And Hunter decided to show up today.
Better late than never.
Okay, Hunter is here. Okay.
He's playing basketball, bud.
Okay, those people who came in since the beginning of class, at the beginning of class I started returning labs. I don't think I had any tests to return, but labs to people. Some of these I had returned last time, but still people weren't here then. So if you came in late and didn't get some labs today, see me either during, after class or in between when we take a break, and let me get some of your work back to you so I don't have to carry it around. Okay, so let's talk about what we're doing. We're in Chapter 8, and today in Chapter 8 we will continue. Won't go any past 7:15. Okay, we may actually stop a little earlier than that, but we will continue in Chapter 8, but I will stop at least 30 minutes before the end of class, and we'll have the test on Chapter 6. Okay?
Do we have a lab today?
Tom, we're not going to test on Chapter 8, are we?
What's that?
We're not going to test on Chapter 8.
Oh, yes, we will. Okay? It will be Tuesday. Remember, I told you before. Okay? I told you before, the final exam consists of 2 parts. All right, and by the way, there was found in here, I forgot to bring it out today, so I didn't have my earlier class. Last Thursday evening, power card table.
That's heavy.
Is that a lot of everybody?
Is that the one where laptops over there?
What's that?
It might be David.
I'll be David's.
David?
David or
What kind of, is it a Dale?
Huh?
Is that a Dale?
I don't know.
No, it's a Dale.
It looks sort of like a, don't say a Fujitsu, it could be.
Let me see. I'll look at it. It says on the.
You said Jiu-Jitsu? Hey,
That's a Fujitsu. Chris decided to show you that.
That was an HP.
Yes. Wait, let me mark Chris here. Chris Lynn.
That's what he said.
All right. That was left, it was found in here after class on Thursday, but I don't know which class it was left from.
Is it HP?
Huh?
HP.
It is HP? Yeah, it does look like an HP plug. Okay. So no one knows if this belongs to someone. I'll try to ask people next week as well. Okay. All right. Now, were there questions?
What do you mean the final is in 2 parts?
Okay, well, I was just trying to explain that, okay? So, let me pick up from there. The first part of the final exam will be your Chapter 8 test. There'll be a regular test, mostly multiple choice, maybe a few fill in the blanks. I don't think there are any calculations on it. Then that will be Tuesday. Wait, I'm sorry, take that back. Okay, we'll talk about that in a minute. The second part of the final exam will be the comprehensive part. That will be matching. Very easy, very quick, no more than about 20 questions, probably fewer, I don't remember exactly. 1 page, matching. Probably won't take you 15, 20 minutes to do, okay? That's the comprehensive part. So the final exam, 2 parts, Chapter 8 test, and then the comprehensive part. All right. Now, so today we continue in Chapter 8, okay? I was explaining to people earlier, the copier's out. So I was able to make copies of Chapter 6 tests. We will have that today. The last 30 minutes today will be that. But I just didn't feel, I felt too guilty to make out copies of the lab. I didn't think we were going to finish the chapter today anyway, but, you know, since I was borrowing somebody else's computer and the lab isn't technically until Tuesday, I just didn't make out that. So if we finish the chapter today, we won't do the lab today, we'll do that Tuesday, okay? I have a feeling we may not finish the chapter today, or we may come really close, I don't know. But the lab will be Tuesday. All right. So let me go over just a little bit of my schedule Today we're in class until, if it takes that long, 7:45. I'll be here until 8. My guess is we'll probably end a little early today. You'll take your test and go home whenever you're through with your test. Okay. What's that?
About 4 o'clock.
Okay, slap him too. He's still dreaming also. Someone must be
He said that
taking.
to me.
Yeah, okay.
Okay.
Yeah. Samuel said he'd slap you. Okay. All right.
He don't want to.
All right. Friday, tomorrow, I'm on the Birmingham campus, 7:45 to 11:45. Now, most days I'll tell you when I'm out there, I say, or later, I don't leave right at 11:45. Tomorrow, I've got an appointment. I think it's at 1 o'clock. I've got to get home, get something to eat, probably change clothes, and get to the appointment by 1. So I'm going to have to leave very close to 11:45, maybe a few minutes over, but I can't just dawdle tomorrow. I've got to be away from campus fairly early. Okay? Now, starting next week, full-term classes are on final exam week, so there are no more classes to speak of. Y'all have got a class because you're a mini-term class. So on Monday, I've got, and this is sort of a hybrid, I'm actually doing a review session for those students in my Math 100 class who want to continue a review session. Other students may opt to take the final. That's when it's scheduled. They can take it if they want to, but I think the majority of them will want to do the review session. Okay? So that will be Monday from 8 to 9:50, almost 10 o'clock. Okay? After that, those students, the Math 100 students, can take their exams anytime they want to. So that means I will not know when I'm going to be given an exam and when I'm not. I know when they're scheduled, but I may be giving them to that 100 class. It's my biggest class, so that could be any time during the week. Okay, so from 10 o'clock, basically, until 5:15, I will be either in my office grading papers like crazy, or entering scores, whatever I'm doing, or I'll be administering a final exam to those Math 100 students, whoever comes by, whenever they come by. Now, when I do that, not a regularly scheduled one, I find the closest classroom to my office and give the exam there. That way I can go back and forth to my office. I don't have as far to go. I can maybe even hear my phone ring if it's ringing. And so from 10 o'clock until 5:15 on Monday, I'll be either in my office or in some classroom between 265 and this room 255, somewhere along there. Tuesday, 8 o'clock, I've got an exam in this classroom, and it will probably take pretty close to the full hour and 50 minutes. So I plan to be here from 8 to 9:50, but after 9:50, I'll be in my office until our class at 3:15. We do meet at 3:15 on Tuesday. Now we'll see what we're going to do on 3:15 on Tuesday, how far we get today. So we'll decide from there. So that's 3:15 on Tuesday. Now, I'm guessing that day if we get the majority of Chapter 8 done, or even all of Chapter 8, then on Tuesday all we'll have to do is the lab for Chapter 8, and it's a paper lab, and possibly the test on Chapter 8, if you want to take that. And then I'll give you all the option of whether you want to take the final that day or not, too. That's completely up to you. You don't have to. You can wait and take it anytime after Tuesday. Wednesday, I have no final schedule, so anytime between 7:45 in the morning and 3:15 in the afternoon, I will be either in my office or in some room in between my office and here. Thursday, nothing scheduled in the morning from 7:45 until 3 o'clock. Now, if you are going to take the exam here Thursday at 3, when it's normally scheduled, it's not 3:15, it's 3 o'clock. I don't care, you can come at 3:15, that'll be fine, but it's at 3 o'clock. It's when technically it's scheduled, and come anytime. You can come before that if you want to, you can come then, okay? So that will be that, and it won't take you more than an hour to do the the last test and the final, I'm pretty sure. And then after that, I'll be back in my office until 8 o'clock. Friday of finals week, I'll be back on Birmingham campus, 7:45 to 11:45. Okay, grades are not due in, I can't remember when they are exactly, either Monday at noon, Tuesday at noon. I don't think it's as late as Wednesday at noon. I believe it's Monday or Tuesday at noon. Now, the reason I'm telling you that is that, I don't know if y'all are aware of this, they shut down Student Suite during finals week until final grades are in. Okay? Why?
Yeah.
Because we only have, our archaic old system we have here only has, like, at one time, 16 portals for people to be on at one time. Okay?
Only 16 people can go in student.
They may have increased it to 32, but that's all. And the first time they ran into this during the finals week, of course, all the students were on Student Suite trying to see their grades. Okay? Not all of them could get on because we only had a limited number of portals. But guess what? The faculty members couldn't get on at all because all the students were in them. And we couldn't get the grades in, and the students were getting mad they couldn't see the grades. We were furious because we couldn't put the grades in. It was a mess. So they decided to shut down Student Suite during finals week until final grades are due, which are either noon on Monday or noon on Tuesday. So don't try to see your grades during finals week. However, I know myself and most other instructors first put the grades on Blackboard and then put it on Student Suite. So therefore, Blackboard, unless it craps out like it does sometimes, it's open all the time. You can always see your grades there. They'll be there before they'd be on Student Suite anyway. And then after finals week are over and grades are in, you can check Student Suite anytime you want to. So just to let you know, Student Suite is usually closed during finals week until grades are due. All right. Now, okay, any questions? Any other questions? That answer most of them. Okay, and again, your research papers are due by Tuesday. If you can get them to me today, if you can get them to me tomorrow, if you can get them to me Monday or Tuesday, I'd greatly appreciate it. The sooner the better, okay? All your work that you may be missing, tests and labs, get those to me before class on Tuesday. Because during class on Tuesday, the first part of class, I will be returning every one of these papers. Once I've returned these, too late to turn something else in. Too late to finish another test. Get it done before class on Tuesday. Everybody understand? Okay. And then Tuesday, we'll have the last class, whatever we're doing in that, and you can decide how much or how little you want to do, when you want to come back, do the final, whatever. That's all up to you. So let's see, any questions before we get going? Okay, what we'll do now is see how, yes.
Can I get the laboratory 11 or whatever?
Okay, the last one we did?
Yes, sir.
Okay, there were a bunch of people who were not here, so let me find those.
Remember I came, but I told you I had to leave.
Pardon me?
Remember I came, but I told you I had to leave.
I didn't give you one?
No, sir.
Okay. Somebody came and I gave them one. I couldn't remember who it was, though. Okay.
Yeah, that was me.
Okay, I thought it was. Okay. All right. Who needs the lab 11? Electromagnetism. Anyone else? Okay.
And that was from Tuesday, right?
Yeah, this is
Okay, thank you.
Tuesday. Anyone else need a Tuesday's lab? Kedrick
I
and...
need the answer guide too, please.
What's that?
Nothing.
Okay. All right. All right, any other questions? All right, let's get going. We left off last time on page 206. We barely got a few slides done. In chapter 8, on 206, we were talking about John Dalton's atomic theory. Okay? He went back to the notion of Democritus, which was about 2,000 years before he did it, and said, yes, matter is made out of indivisible atoms. Okay? He did this based on the fact that compounds are formed by what they call laws of definite proportions, which indicate there are certain particles that can combine together in certain ways. Now, elements. Okay, now again we're talking macro and micro. Atoms are the microscopic things that go together. An element is the macroscopic concept. An element is made up of identical atoms. Iron. If you have a piece of pure iron, every atom in that is iron. Okay? If you have a piece of copper, if it's pure copper, every atom in it is copper. Okay? Of course, something like wood, made out of carbon, oxygen, hydrogen, no. It's not an element. An element is made of identical atoms. Different elements, was there a question? Okay, different elements have atoms with different masses. Okay, an iron atom has a different mass from a copper atom. Hydrogen atom has a different mass from oxygen atom. Every atom has a different mass. Now, for those who may already be looking into it, let me see if I can get my book without picking up every piece of paper. If you have the back cover of your book, you will see the periodic table here. We're going to come to this later in the chapter 2. It's in the chapter 8. So if you don't have this book, you'll find it in chapter 8 too. On the table here, the periodic table, there's hydrogen, there's helium, there's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, and so on and so on. Okay? These are the elements. Okay? Every element has a fixed number of protons. Give me a number.
43.
43.
2.
The element with 43 protons is, you would have to pick this one, technetium. Okay? Never heard of it before.
What's 27?
Okay? 27?
24.
Wait. 27 is cobalt.
What's 7?
What's that?
27.
Wait a sec.
Did someone say another number?
21.
21? 21 was scandium. Okay? Every element has a fixed number of protons. Now, elements can have variable neutrons, but it's usually within just a few numbers of each other. So their average atomic weight or mass is also going to be pretty close to the same. Maybe off by a little bit, but that's why it says here different elements have atoms with different masses. Okay? Now, chemical compounds are made of atoms at specific integer ratios. That's what I was talking about. Dalton used to come up with the idea that we're back using atoms again. Okay? For instance, carbon and oxygen combine at a 1:2 ratio, 1 carbon for 2 oxygens to make carbon dioxide. Where if you have 1 carbon and 1 oxygen, you have
Carbon monoxide.
monoxide, poisonous, deadly. Okay? Carbon dioxide you don't want to breathe either, but carbon monoxide will kill you. Okay? 2 hydrogens, 1 oxygen will give you water. 2 hydrogens, 2 oxygens will give you hydrogen peroxide. No, hydrochloric acid had chlorine in it.
Yeah.
One hydrogen, 1 chlorine would be hydrochloric acid. So they combine at specific integer ratios, but they will be atoms from different elements. From different elements. That's what makes chemical compounds. All right? Atoms are neither created nor destroyed in chemical reactions. They're just combined or separated in various ways. That's what goes on in a chemical reaction. You never create an atom, you never destroy an atom. Mass cannot be created nor destroyed. Okay, those are the 5 features, major features of Dalton's atomic theory. And they hold true to this day very nicely. All right. Now, in the late 1800s, I think it was around 1890s or so, J.J. Thomson, a physicist, performed some what they called cathode ray experiments. Anyone know what a cathode ray is?
You want me to guess?
Yeah, you can. Okay. Basically, cathode rays can create X-rays. They don't always, but they can. A cathode is a positively charged electrode that then is going to attract electrons. Or it's a neutral one that gives off electrons, one or the other. And anyway, J.J. Thomson was working with a cathode ray, something that looks like this, not quite, it's a really simplistic model. There's the cathode, and here's the anode. Okay? This is, all right, I may have said it backwards, but I think they may have it backwards too. But anyway, you have the cathode rays coming down here, going from the cathode to the anode. You have a vacuum pump there, so you don't have any air in there. Basically, all you have are the particles. Okay? Now, in dealing and playing around with this some, he discovered that there were negatively charged, tiny, incredibly tiny little particles that I think he actually may have named them, but someone else did may have electrons. Whereas protons and neutrons, great, big, massive things compared to electron, about 10,000 times more massive than an electron. Yet a electron has a single negative charge. A proton, though it's hugely more massive than an electron, like 10,000 times more massive, they single positive charge. Whereas neutrons, no charge at all, but they're about the same mass as a proton. So J.J. Thomson discovered these negatively charged particles, and they were ultimately, maybe he or someone else named them an electron. Now, he was able to determine their charge to mass ratio, but he was not able to determine their mass. He could tell how much charge they had per unit mass, but he couldn't tell what the individual electron's mass was. He identified the electron as a fundamental particle. What do we mean by that? You cannot break an electron down into anything smaller than an electron. Nothing. Same thing with protons and neutrons.
Pretty small.
They are incredibly small, and they have a single charge. If you broke it down, then either some piece would have a charge and some not a charge. You can't have half a charge. That's as small as you can go. It's a fundamental particle. Later, we determined protons and neutrons were also fundamental particles. So he discovered the electron. Late 1800s. Okay? Here was basically his experiment and how he was able to determine that. What he had was a cathode source here, source of movement of particles, and let's call them electrons. They're coming from the cathode ray, okay, going toward the positive side. Here it is. But they were flying through it fast enough, and then he had charged plates here, electric charges, a positive and a negative, okay? He also put it in a magnetic field. They switch north and which one side south, okay? So he had charged plates here that basically collimated the electron beam, and he also had a strong magnetic field going in the opposite direction. And then he had a detecting screen here at the end for these rays to come down. And he found that the deflection depended on the charge to mass ratio. So he measured how much they were deflected and came up with a good number for the charge to mass ratio, but he couldn't determine either the charge or the mass. He didn't know the charge, and he couldn't determine the mass. It was way, 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 way too small. Now, positive and negative charges were deflected in opposite directions. Some went up and some went down because of these charged plates here. The positive plate would draw the negative charges up here. The negative plate would draw the positive charges down there. And he probably also detected that they were deflected at different angles, but we won't get into all that. That was his cathode ray experiment. Playing around with some new technology, learning all sorts of things, not being able to nail it all down, but making some pretty important discoveries on the way. Okay? Now, about 10 years later, a guy named Robert Millikan did a pretty famous, what they call an oil drop experiment. Okay?
Did you drop some oil?
He dropped some oil. Okay? Close. Okay? What he had was a two sets of plates. The top plate had a single little hole in it. Pretty small hole. Okay? The top plate he charged with positive charge, set up a battery. Now, their battery is backwards. Okay? Should turn that around. Positive plate here, negative plate there. Remember our convention, the big line is for the positive, the small line for the negative. Okay? So he set up a strong electric field there, and he had oil in a little, almost like a perfume sprayer. Okay? It's called an atomizer. Okay? Made tiny, tiny, tiny little droplets. Okay? Now all this is under vacuum, so hopefully there's no air in there, none to speak of. And it did have a port, and he had a viewing scope that he could look through the port, and the lights were coming in at different angles so he could see when the droplets were falling. Okay? Now, under their own mass, of course the droplets would fall, right? Gravity would be pulling them down. But you had these electric fields here, so some of these oil droplets would pick up a charge, an electron charge. Okay? And because the positive plate was on top, the negative plate on the bottom, what would an electron tend to do? Which way is the electron going to go?
Down.
Why?
The other one's going up.
Negative plate down here, positive plate here. Electrons are what charge?
Negative.
Negative. So they're going to go down?
No.
No, they'll go up because like charges repel, unlike charges attract. So this droplet that would have been falling and maybe was falling, and he could see it falling, all of a sudden would stop falling and start moving up again. Okay? Now his viewing scope also was calibrated, very fine little grid on there, magnified, and he could count how many millimeters, or yeah, I think it was millimeters, it was going, and he had a clock, and he could tell how fast it was going, or estimate how fast it was moving. And depending on how many electrons that droplet picked up, it could just slow its drop, it could stop, or it could actually move up. And he found that they went by discrete numbers. All the droplets basically, and they were about the same size, all moved at a certain set of speeds. Nothing in between, certain set of speeds, depending on how many electrons that droplet picked up. Okay? So, and when I went back to grad school at Georgia Tech after I finished in the Navy, I needed to take 4 courses, or I wanted to get my GI Bill. That was 12 hours, was kind of the full load. And I was able to find a few courses I could take, and there just weren't that many being offered. It was a winter term. And I found a physics lab that I could take, graduate physics lab. I took it, and we did like 4 or 5 of it. I had a guy that I was a lab partner with, and we, one of the 4, I think it was 4 or 5 experiments we did, one of them was Millikan's oil drop experiment. And I mean, I literally saw the droplets falling, stopping, going up. You could just tell they were picking up electrons. That was what was creating that. So therefore, he studied these charged oil droplets in an electric field. The charge on the droplets was a multiple of the electron charge. They could pick up 1 electron, 2 electrons, 3 electrons. They couldn't pick up 3.5 electrons. No, it was fixed numbers. Now, according to that, he could get the least number of charges, and now combining with Thomson's cathode ray experiments, now he could actually determine the rate of electron mass. Thomson came up with the charge to mass ratio. Since he now could get a charge, he could now calculate the mass and found out it was incredibly tiny. And we did the same thing. I can't remember what our precision was. We came pretty close. We came pretty close to measuring the mass of electron without ever measuring the mass of electron. There's no scale made that you can measure an electron falling on it and tell any difference. That's so incredibly small. But because of all the knowledge that we had, you could deduce the mass. Pretty incredible experiment. Robert Millikan, his famous oil drop experiment. He dropped some oil, okay? So Thomson's result was that the charge to mass ratio was an incredibly small number, 1.7584 times 10 to, actually a big number, of 10 to the 11th coulombs, that's charge, per kilogram, charge to mass ratio. Why is it such a huge number? Kilogram is a lot of mass, okay? This book is about a kilogram, maybe a little bit more. That's a lot of mass. And you think a coulomb is a pretty small amount of charge, so it takes a lot of coulombs for 1 kilogram of mass. It would have made a lot more sense to use grams, but they use kilograms, SI. Okay? Millikan's result from his oil drop experiment gave that the charge was actually 1.6 times 10 to the minus 19 coulombs. So if you combine these experiments, then you could calculate what the mass of an electron was. No way you could ever measure something 10 to the negative 31 kilograms. No way in the world. But you could calculate it, and sure enough got to divide this by that, and you get 9.11 times 10 to the minus 31 kilograms. So even if you measured in grams, that would be 9.11 times 10 to the minus 28 grams. Or milligrams, 9.11 times 10 to the negative 25. You're still at such tiny little numbers, there's no scale in the world that will measure that kind of precision. But you could calculate it, and that's what they did. Make sense? All right. So let's move sort of back again. Some early models of the atom. Dalton's basically said atoms are indivisible. Thomson and Millikan, their experiments determined that they had incredibly small little particles in an atom. Electrons, the mass is very, very small. No measurable volume. No way we've been able to get the volume of an electron. It's just too incredibly tiny. So what's the nature of the atom's positive charge? Well, Thomson, and by the way, there's a bunch of Thomsons out here. This is not William Thomson, who was Lord Kelvin. This was like a century later, okay? But this is J.J. Thomson. So J.J. Thomson had a model. Now remember what models are? Let's go back to Dalton. Dalton figured that atoms and combined in certain ways. So his model, and he knew this probably wasn't true, is that every atom had so many hooks on it. So carbon, for instance, would have 4 hooks. Oxygen would have 2 hooks. So this oxygen would combine with 2 of those, and another oxygen with another 2, and that gave you CO2, right? And oxygen has 2 hooks, hydrogen 1 hook, 1 hook here, 1 hook there, H2O, there's water, okay? So he said, look, it makes sense. He didn't really think there were hooks. That was the model he used. Well, similarly, Thomson came up with what they called the plum pudding model. He knew electrons were tiny, were incredibly small, but had a fixed charge. So he said, well, let's just imagine that an atom is made up like a plum pudding, that most of it's pudding. We don't know what the pudding is, but the plums are these tiny little electrons in it. Think of that as raisins, or even small, okay? Maybe even poppy seeds or something like that. Something incredibly small in there, and that everything was that. So that was the model that he was based on. He couldn't tell anything else. In other words, electrons are embedded in a blob of positively charged matter like raisins in a plum pudding. That's exactly the analogy he used. So it's not really plums, it's raisins. Okay? Now, Ernest Rutherford, maybe 1 year after Millikan's oil drop experiment, said, okay, let's measure that a little bit. Now, one of the biggest atoms that people had some sort of access to was gold. Gold, by the way, here is number 79. Okay, more than halfway down the periodic table, about 3/4 of the way down the periodic table. A big, massive atom. Now, gold may not have been quite as expensive then, but it still was an expensive thing. But one really neat thing about gold is very malleable. What does that mean? Basically, it's a very soft metal. Now, if any of you have a gold ring, how do they measure the gold in the ring?
Carats.
Carats, exactly. This was probably, I'm guessing, 14 karat. Okay? Pure gold would be more like 24 carats. But they don't make much jewelry out of pure gold, or at least we don't. The Indians, like subcontinent Asia Indians, they tend to make a lot of very pure gold jewelry. We have some very good Indian friends, and Nalini, when she goes to India, she not always, but quite often will bring back to my wife, because they're really good friends, some sort of gold jewelry. Okay? The problem with pure gold jewelry, it stretches because it's very malleable. You put other alloys with it, and it keeps its shape pretty well. But if that was a pure gold ring, if I hit it on the wall too hard, it would probably bend it. Okay? So, and then I might not be able to get it off my finger. So most U.S. jewelry is 14 karat or so gold. In India, they actually use really close to 24 karat gold. So gold is very malleable. It's a soft metal. You can shape it very easily, but you can also roll it very easily. Okay? Just like you do aluminum foil, you can roll it into incredibly thin sheets of gold. In fact, have you ever heard of gold plate? I think is what it's called. Some of the medieval things, icons and paintings and stuff like this, they look like they're pure gold, but they've just taken some other substance and then just put the foil, gold foil on it. Looks like it's pure gold, but it really isn't. It's gold, but a very, very thin layer. That's what we call gold foil. So Ernest Rutherford was scattering some alpha particles. Anyone know what an alpha particle is? No, it's basically a helium nucleus. It's 2 protons, 2 electrons. So it has a +2 charge. Protons have 1 positive charge each nucleus. Neutrons have no charge, so it's a +2 charge. And by the way, it's a type of radioactivity too, but it's usually not very, can be dangerous, but usually not too bad. Okay? Paper will keep alpha particles from reaching you. Okay? So they're not good. So he was playing around with alpha particles, and he was shooting them through gold foil. Okay? Or that's what he thought he was going to do. But remember, in Thomson's model, gold was a plum pudding. So probably not many alpha particles would make its way through because of the pudding. Okay? Surprising for Rutherford, most of those alpha particles went right through the foil. Right through. No pudding there to stop them. A few, however, were scattered backward at a huge angle. Okay? Others were scattered at different angles. Okay? And what was his conclusion from this? That the atom's positive charge resides in a tiny, incredibly tiny little nucleus. Not in the pudding of a plum pudding, but in a tiny, tiny, tiny little nucleus, but very massive nucleus. Now that sounds like it's contradictory. The volume is incredibly small. The the mass is incredibly large, okay, for that smaller thing. So most of the positive charge was in tiny little nuclei. So the rest of it was made up of that electron cloud. Nothing there. Just these tiny little electrons flying around, so that these alpha particles just went straight through. Except occasionally they would hit a nucleus and bounce back, because they were both positively charged. And of course, the gold nucleus is huge compared to a helium nucleus. So the conclusion is the atom's positive charge resides in an incredibly small but very massive nucleus. Okay, later they discovered the positive charges were, and they named them as protons. And James Chadwick, about 25 years later, also discovered these neutral neutrons in the nucleus. Neutral neutrons in the nucleus. Okay, is that enough end words for you? Okay, James Chadwick did that. This was sort of what that experiment looked like. Here was his radioactive alpha source, and he had them collimated and stuff, so they came out at relatively, straight line. Here was his gold foil, and he was expecting to see most of the alpha particles being reflected back. There was just a tiny little gap there. What he found, most of them came straight through, not a problem. A few of them got deflected a little bit, and a few got deflected really big time. And what was the conclusion? Those positive charges resided in an incredibly small positive nucleus, but very dense. So here's the model, folks. Let's see if they say any more. Okay? Here's the model. And this is even exaggerated. The nucleus, which has basically all the mass, just about all the mass, is the tiny, tiny, tiny little thing there. And around the nucleus is an electron cloud. Just a cloud of electrons with hardly any mass at all. And certainly hardly any volume at all. So most of these alpha particles made it straight through. Every now and then they hit a nucleus head on and then bounce back at various angles. But the vast majority just made it through unscathed. Now, I can remember my older brother when he came back from Georgia Tech after his freshman and sophomore year I think it was. He was 2 years older than me, so I was a senior in high school. And he had taken a physics class, and his physics professor had used this term, and Mike thought it was so cool. He said, most of everything is nothing. Okay? It sounds bizarre, but if you think about this, gold, which is a very dense metal, most of gold is, the mass is right there in the nucleus. Most of the rest of it is empty space. The vast majority, even this one of the densest metals out there, vast majority. Yes, all the mass is located in a tiny, tiny little nucleus, and everything else is empty space. It's kind of like the stars and the planets and the moons and the solar system. In between, there's nothing. Okay? Absolutely nothing, or almost nothing. And that's basically what we have. Most of everything is nothing. Where there is something, it's awfully dense. Okay. All right. Now, there is a nice little blurb at the top of page 208 and 209. The discovery of the electron. Several other people are mentioned here. The cathode ray tube was originally called Crookes tube because of an English physicist named William Crookes. And by the way, folks, like I said before, barely half of you have turned in a paper yet. This chapter is packed to the gills with potential paper topics. I mean, already we've talked about John Dalton. We talked a little bit about Aristotle last time. We talked about J.J. Thomson. We talked about Crookes, who developed the cathode ray tube. We talked about Ernest Rutherford, John Millikan, or Robert Millikan. I mean, you got tons of people here. Protons, electrons, there's so many things. So the If you haven't found a paper topic yet, this chapter is full of potential paper topics. So let's look at the atomic number. Atomic number is the number of protons in the nucleus. Does that ever change? Do you gain or lose protons in the nucleus of an atom? No, that would take a nuclear reaction to happen. We hope those don't happen, okay? Number of protons is fixed. What were some of the numbers you gave me before? Give me a number.
42.
42. 42, was that the same one? No, that was molybdenum.
No, we was looking at 27.
Okay, 27 was cobalt, okay? If it has 42 protons, it's always and ever molybdenum. If it has 27, it's always and ever cobalt. Can't be anything else, okay? So the number of protons determines what element you're talking about. That atom cannot gain or lose any protons. So the elements are distinguished by that atomic number. Now, when this slide was done, they said 113 elements have been identified. The book lists now, I think, 118. But some of these are maybe unidentified. So maybe that is still good for 113. That's all that we've discovered so far. That doesn't mean they won't discover some more, but that's the vast majority of it. The number of protons equals the number of electrons in neutral atoms. But what if an atom is not neutral? Either it's positively charged or negatively charged. Positively charged means, has it gained a proton? No, you never gain protons. It lost an electron. If it's negatively charged, does that mean it lost a proton? Never, okay? You gain an electron. So you get the charges by other things, okay? Gaining or losing electrons. But in a neutral atom, number of electrons has the equal number of protons. Otherwise, it wouldn't be neutral at all, okay? So, are all atoms then identical, say, of cobalt or molybdenum or anything else? No, because they can have different numbers of neutrons. Can have different numbers of protons, those are fixed. You can have different numbers of electrons, but they are almost massless, okay? So then they're not neutral atoms, they're ions. If they're positively or negatively charged, they're ions. But what an isotope is, iso means same element, but with a different mass. And how that happens is different number of neutrons. Because a neutron does not change what the material is. Well, let's take the simplest one. What is the lightest, smallest atom we have? First thing on the periodic table. Hydrogen. Okay? Most hydrogen, there's a little bit of hydrogen in the air. It's in water vapor. It's in things, very little pure hydrogen there. But if every hydrogen out there, the vast majority is a single proton and no neutrons. No neutrons. Just a single proton with a single electron flying around it in a cloud. That proton's in a tiny little nucleus, and the electron, where it's incredibly small, is just floating all the way around. That's what hydrogen is. You can't get any simpler than that. However, not all hydrogen is like that. Very rarely, like maybe 1 out of every 100 or 200 or something, hydrogen atoms will have a neutron. But what's that done to the hydrogen? Doubled its mass. Doubled it, okay? And so they call that deuterium, okay? And then 1 out of maybe 10,000 or so will actually have 2 neutrons. And that's triple the mass of this one, so that makes tritium. Okay? Now, how we distinguish between the 3 of those, you put H, that stands for hydrogen. That's the only thing that will be H, hydrogen. Okay? Oh, and here we have Chris. and we have David. All right. Now, some people, before you go somewhere, did you go? That's it. Is that yours? Okay. It was found here last Thursday, and you weren't here Tuesday, so they couldn't ask.
Yeah, I think it is.
Okay, it was found right over that area, and I think you were sitting over there. Okay. All right. So the element's symbol for hydrogen is H, helium is He, beryllium is Be, boron is B, oxygen is O, whatever it is, that goes here. The subscript to that is how many protons. Hydrogen will always have a 1 here. Always have a 1 as a subscript, and it precedes it. The mass number is how many, the total of protons and neutrons. We don't even count electrons. Of course, number of electrons, if it's neutral, it's going to be the same as the number of protons. But they're so terribly tiny, we don't even count them for mass. So the mass number will be, the number up here is how many protons plus neutrons. So if it has one proton plus neutron, that means no neutrons. One proton, 2 protons plus neutrons, 1 neutron. 1 proton, 3 protons plus neutrons, that means 2 neutrons, obviously. Okay. Now, what difference does that make? Not much. Water is still water, or hydrogen is still hydrogen. Doesn't change much, except the density changes. Now, people are very interested in this high density hydrogen when it combines to make water. They actually give that water a name. If the water has very much deuterium or tritium hydrogen in it, they name it heavy water. Okay? Because it has extra neutrons. Who's interested in having extra neutrons? Nuclear power people. Because neutrons can absorb some of the nuclear energy to keep things from blowing up. And that's what they do. So if you'll notice, most nuclear power plants, and I would say all nuclear power plants, are right near water, right along a major river. In Japan, they did it near the ocean. They regretted that when they had a tidal wave knock out Fukushima. But in that water, they're always using it to cool, because those nuclear power plants produce an awful lot of heat. So using the water to cool, and that's why you'll see these huge cooling towers. All they're using it for is to cool that off, because the water that goes back, they want it closer to what it was originally. But the other thing they're doing, they're always trying to extract with the centrifuge any heavy water they can get. Remember, it's only 1 part out of 100 or out of 10,000 or something like that that will be heavy or hydrogen. But they get that heavy water and they fill their tubes with that, and if they're trying to slow down the reaction, they push those tubes in. That slows down the reaction. If they need to speed it up, they pull the tubes out. I don't know if you ever watched Star Trek. They used to push the tubes in and out. That was way back. Okay. But that's really how they do that. Okay? So there is a sample. Pick any element you might choose, and you can write it in that kind of a notation. The different isotopes will be the same atoms with different number of neutrons. For instance, hydrogen has 3 isotopes: hydrogen, deuterium, and tritium. Okay. Most of the rest of them don't have their own names. They just say carbon 14, carbon 12, carbon 11, something like that. Okay. Any questions on that? That's what an isotope is. Iso means same. Same element, different masses. Different masses come from different neutrons. Numbers of neutrons. So, what about these atomic symbols and their masses? The mass number is the number of protons plus neutrons. That's in the superscript number. The atomic mass units, that's what we use to measure that. They have to have a standard. And they took one of the most common materials out there, carbon, 12. Most carbon has 12 mass, mass of 12. By the way, anyone know what the atomic number for carbon is? 6. Okay? And if it's got a mass of 12, what does that mean? It has what? If it has 6 protons, that's the atomic number, and its mass is 12, what does it have? 6 neutrons, exactly. That's your common carbon 12. Okay. Has anyone ever heard of carbon dating? It's like Matchcock. No, that's a different kind of dating. Okay? Okay, what carbon dating is measuring, because there is another carbon that has 2 more neutrons, making it 14, carbon 14. Carbon 14 is actually radioactive. Not very strongly radioactive, but slightly. But if something's radioactive, you can detect it really, really easily. Okay? Now, how does it get radioactive? Well, in the outer part of our atmosphere, there's carbon up there, carbon dioxide or methane or something else, and it's getting bombarded with cosmic radiation, gamma radiation from the sun. In fact, that sphere out there, it's called the ionosphere, is blocking that from coming to Earth. That's why we don't get fried. That's why we can live on the Earth, because our atmosphere blocks most of that harmful radiation. Never makes it to Earth. But what's getting hit are the atoms that are up there, including carbon. And some of that carbon is getting energized and picks up a couple of neutrons. Okay? So you always have about the same number of carbon-14, the same percentage of carbon-14 atoms in the atmosphere. It's not very many, probably less than 1%, maybe tenths of a percent. You know, a tiny amount of carbon-14. And what uses carbon?
Lights.
Trees, grasses, plants. Squirrels, okay. They breathe in carbon dioxide and they make simple sugars, right? Those simple sugars get combined to make complex carbohydrates, like cellulose. And over years and time, that cellulose will then form into other things, so, other material. So everything that's organic, that was one time living, plant or animal, every cell in it has carbon in it. Every one. Now, at the time that tree is out there breathing and making wood and stuff like that, it's exposed to the carbon-14 in our atmosphere. All at pretty close to a fixed percent. But once that dies and becomes fossilized, okay, whatever happens to it, and then so many years later, you may have a seashell or anything else. Over the time, that radioactivity has died down because radioactivity decays, and a half-life of maybe a few hundred years or something like that. So after a few hundred years, you only have half as much carbon-14 in that material. After it's dead, after that thing has died and deposited. And then in another few hundred years, half again as much. So what they can do is measure how much carbon-14 is in a given fossil, and then put it on the curve and see how old that fossil is. Because you know that the carbon-14 decayed at a fixed rate. Okay? And that's called carbon dating. That's how they estimate how old artifacts are, that have any kind of organic matter in them. Yes?
Do you ever think they'll be able to produce something?
Okay, I can do that again.
Do you think they'll ever be able to produce synthetic food?
They probably can. I'm guessing someone can, but it probably costs more to produce than you can get use out of it. I don't know for sure. I know they can produce synthetic diamonds, but it's such a huge expense. Find real diamonds is cheaper and expensive as they are. So possibly, all it takes is heat, pressure, temperature, increase things. What's that?
It makes you wonder if they can do everything else.
Yeah, and if someone ever perfects the concept they may make some money on it. Yeah.
You think they'll be able to like make a substance you can do to like reduce the radioactivity? Make it dry down faster?
I don't know that that can be done because, again, that's a nuclear reaction that's controlled strictly by the forces within the nucleus. And we don't have much control over those. So I don't know the answer to that. So far, I've never heard of anything like it. Okay? It'd be nice to know. But actually, most of the time, we would want it to react faster. Because right now, and we talked about this in my morning class, y'all heard of Chernobyl? Okay? Chernobyl was a Soviet, there's a town where a Soviet nuclear power reactor was, and Soviets were notorious for not having really good quality control and not really good backup systems. It went out of control, and they had a major meltdown. Okay? Have I talked about that before in this class? Oh, I have. Okay. And we talked about the elephant foot. Is that what it was called? That pile that's left there. In our class this morning, it was a math class, pre-calculus algebra, when we were doing exponential decay. Okay? If you had 10 pounds, and they use this, 10 pounds of plutonium, it doesn't sound like much, does it? But it's deadly. Okay? The half-life for plutonium, 24,100 years. So for that 10 pounds, let's say we had 10 pounds of plutonium left over after Chernobyl that they don't know what to do with it. It'll take 24,100 years for that to decay down to be 5 pounds. Okay? And then another 24,100 years before you get to be 2.5 pounds. And another 24,100 years for it to be 2.5 pounds. And another, you keep on going. We did the calculation on it this morning. 100,000 years later, you still have more than half a pound of plutonium there, which is probably enough to kill you. Okay? 100,000 years later.
How many?
100,000. Okay. And guess what? Our nuclear waste, we talked about this before too, didn't we? It's being shipped down, I think, to Utah. I think they're still putting it in Green Mountain, White Mountain, stuff like that in Utah, burying it way underground, really strongly sealed containers. How long are they?
There's nothing in Utah for it.
Say again?
So that's okay. There's nothing in Utah for it.
Okay. Tell the Native Americans that, that live there, and a few Mormons, they may want to disagree with you a little bit. Okay.
Sorry,
Anyway.
didn't mean to offend you.
All right. So anyway, that's why carbon-12 is used. Very common atom. 1/12 of this mass is called 1 atomic mass unit. Now, back when I was in school, we called them AMUs for atomic mass units. Now they just call it U's, a unit, which to me is a little weak, okay? But that's what they're using now. The atomic weight is the atomic mass of an element averaged over the naturally occurring isotopes. So hydrogen, for instance, you have lots of hydrogen, just one AMU, or U. But then you have a few deuteriums, which are 2, and a few tritiums, not very many, 3. You average those all over the naturally occurring isotopes. And so hydrogen turns out being, if you look at hydrogen in the table, is 1.008. So that means 8 out of 1,000 hydrogen atoms is going to have an extra proton. Neutron, not proton, neutron. 8 out of 1,000, okay? And probably 1 out of a few million will have 2 extra, extra 2 neutrons. That's how you do those averages. Okay, and again, here's our symbol. That's the same thing we saw before. Most of the hydrogen is this. Okay, maybe 8 out of 1,000 would be this. And maybe 1 out of 1,000,000 or fewer than that would be this. So it averages out to be very close to 1. Very, very close to 1. All right. Let's take nitrogen, for instance. Nitrogen has 2 naturally occurring isotopes. Nitrogen 14 is the most common. Nitrogen 15 has 1 extra neutron. How many protons does nitrogen have? Well, this is 7. It's number 7 in the periodic table. So how many neutrons does it usually have? 7, the difference between those. But one time out of, what is that, about 800 or something like that, we'll have 8 neutrons. Not 7, but 8. So 99.63% of those will be nitrogen 14. 0.37% will be nitrogen 15. So what you do is multiply this decimal, 0.9963, times the atomic mass of 14.00370 units, atomic mass unit, and 0.0037 times 15.0011 units, and that gives you an average of 14.0067 units. That's what you'll see on your periodic table. I bet you they round it to 14.007. No, 14.01 is what they do. They rounded it here, okay, to 1.01. That's because most of it is this, a little bit is that. But you see, most of it is 14. So you usually look at that number and you have a good guess what the most common isotope is. There are a few exceptions to that. Most notable is chlorine. If you look at chlorine's mass, and by the way, on the periodic table, the number at the top is the atomic number. 1, 2, 3, 4, 5. That's at the top. The number at the bottom is this average number here. So when you get over to chlorine, which is number 17, look at it. 35.45. That means most of chlorine has, and it's a 17, has 18 neutrons, but almost as many of them have 19 neutrons, okay? Because if it was 35 on the nose, that would be 18 neutrons, but it's 35.45, so almost as many 19 neutron as you have 18 neutrons. It's rare to see one that's that close. Most of those are very close to integers. Very few are exactly integers. Okay. So let's talk about our classical atoms. Okay? The predictions of the classical theory is that the electrons fly around the nucleus. Nucleus is incredibly massive, but incredibly small. And the electrons, almost no mass at all, fly around in big clouds around the electron, around the nucleus. So the electrons orbit the nucleus. Now, by Newton's rules, anything that's moving in a circular path has to be accelerating, right? Centripetal acceleration, right? Center seeking. If it's got a curve to it, it's got to be accelerating. Acceleration, charges radiate. Okay, accelerated charges radiate. We learned that in the last chapter. You have a moving charge, changing its motion, you're going to radiate. If it radiates, it loses energy. If it loses energy, it spirals into the nucleus. If it spirals into the nucleus, it dies. So according to classical theory, atoms can't exist, okay? Because you can't have a moving charge around a charged nucleus. It wouldn't happen, okay? But it does happen. Experimentally, atoms do exist. You need a new theory. And this was what happened in physics. Right around the turn of the 20th century. The late 1800s, early 1900s, physicists were sitting back and saying, you know, we just about got it all knocked, folks. We have Newton's 3 laws of motion. We have the law of gravitation. We have Thomson's thermodynamics. You know, we got it all just about figured out. We can just work out a few little details here and there. We got our field covered, and we can just teach it from now on. We understand it. Except for a little problem like this that didn't fit Newton's laws. It said atoms can't exist. Well, we got to figure out what's going on there. And right around the 1910s, 1911, somewhere in there, quantum mechanics were discovered. Okay, this didn't obey Newtonian mechanics. It was a brand new set of rules. Just like Newton's calculus was a brand new mathematics, suddenly quantum mechanics was a brand new physics. Okay, so this is the quantum concept. Max Planck, pretty famous German scientist, around 1900, introduced this concept of quantized energy. Okay? Einstein, another fairly well-known, he was sort of Swiss, sort of German, okay, in 1905, proposed that light is made up of quantized photons, little packets of energy, okay? The higher the frequency of the protons, the more the energetic photons you had, not protons, photons, okay? This was Planck's law. Pretty simple. The energy of a photon is a little packet of light there, is Planck's constant. It is proportional to the frequency, directly proportional to the frequency of that light. That constant proportionality, they found was a constant of nature, named it after Planck, Planck's constant. 6.63 times 10 to the negative 34. Look at the size of these numbers, folks. That is tiny. Joule seconds. Okay? Well, why joule seconds? Because energy is measured in joules, frequency is measured in per seconds, cycles per second. So you need this to be joule for here, and seconds, so it cancels out per second there. So that's what Planck's constant is. Incredibly small number, but that produces a quantum of light. And that's exactly what's happening in those fluorescent tubes. We talked about it before. You have ionized gases flying down those tubes, releasing, with energy, because that charge has an energy. They're ions, they're charged particles, have energies. They excite the electrons in that powder, that phosphorescent material that coats the inside of those tubes. It excites that, and it jumps up one energy level. That's called a quantum, one little energy level, okay? And when it jumps up, when it passes, once it passes, it falls back. That fall back gives off one photon of light, and that's why that produces light. Incandescent bulb, it just gets so hot, it glows. That is actually producing a little quantum of energy. Just millions and trillions of them, and that's what gives you light. Yes?
Can we take a break?
Okay, let's see. Yeah, it's getting close to 5. Okay, let me see where we are in the slideshow. Yes, that would be a pretty good place to take a break. Let's see where we are in the text. Okay, we've just started 8.2, and this is the quantum concept, Max Planck, and we'll move then to atomic spectrum next. We do have an example coming up, but let me say this before we leave Max Planck, okay? And this is just a little deal. Max Planck, German physicist, very famous, won the Nobel Prize for his work in this. He started it's a series of universities in Germany that are now throughout Europe. And the reason I mention this is 1 year about, I think it was around 2008, 2009, I think it was. My wife had graduated at UAB in epidemiology, and one of her classmates was a guy from Italy. Especially one blank on his name. But anyway, we were real good friends with him. Fabio Barboni. And
So
his
you're
wife.
not very good friend if you remember the name.
Well, yeah, I'm just terrible with names, Fred. But anyway, Fabio and Rita were good friends of ours. We got to know them. We enjoyed them a lot. They had just gotten married. We had just gotten married. We didn't know how close that was within just months of each other. They were in Italy. We were here. So they came over, and Fabio was brilliant. Just a really brilliant guy. My wife and he interacted really, really well. And so anyway, when they graduated, he moved to Boston. Rita loved Boston. By the way, she went up there and took English courses and stuff like that. Why they replaced it down here. But she loved Boston. So anyway, when they were in Boston, their first child was born, their son, Giacomo. So he was born in the U.S. He became a U.S. citizen, okay, because of being born here. And then Fabio's parents were really giving him a hard time that they were so far away and couldn't take care of him if something happened. So they talked him into going back to Italy. So they took their 1-year-old son and went back to Italy, and then the 2 daughters were born later in Italy. So they weren't American citizens. Well, we kept in touch, not real close, but we kept in touch over the years. And my wife had professional meetings in Italy. Oh, this would have been, I don't know, probably about 13, 14, 15 years later, something like that. And it was right in between terms, so I got to go with her. No, it was on Thanksgiving, over Thanksgiving. Fabio's birthday was the same week as Thanksgiving that year. So, and they had loved the holiday of Thanksgiving. Of course, Europe doesn't celebrate Thanksgiving. So we went over to celebrate Fabio's birthday, and it was his 40th birthday, I think it was. And, you know, his Thanksgiving holiday and stuff, and we met all the family and stuff. And by this time, Giacomo was in early years of high school. And Giacomo and us got along really well. He entertained us some. He was a delightful kid, really brilliant like his dad. And we got along so well that within a couple of years, he was going to be graduating from high school. And his parents wanted him to have the opportunity to go to university here in the U.S., since he was an American citizen.
So he comes to beautiful old Boston State.
No, he didn't. He went to a little-known school up in the Northeast called Harvard, I think it was. Okay, but they need. Oh, wait, I'm sorry. We're talking about high school. Okay, high school. They were looking around for opportunity to do like an exchange or something. But then when it turned out that we got along so well with them, they thought, is there something in Birmingham? And sure enough, right up the road from where we lived was a small private high school. I don't know if any of you have ever heard of Altamont School. It's a nice little school. And they decided to send them there. And Giacomo spent his senior year with us, living with us, and he went to school here. Then he went back to Italy, because in Italy they have 5 years of high school. So he went back. He graduated from Altamont, by the way, top of his class. Okay, and then he went back to Italy and graduated his 5th year there. And then he started looking at colleges, and that's when he came over. Because his mother loved Boston so much, he decided to go to Harvard, which was really a pain in the neck because they don't give scholarships, and it cost his family their house, basically, to send them to Harvard, which we thought was a really bad decision, but they wanted them to have that opportunity.
They were pretty financially stable.
They what?
They were pretty well.
Not after he went to Harvard. Okay.
So what kind of job did he get?
Well, actually, Fabio was head of a department in a university, but the university don't pay as well there as they did here. But they were able to get by, but they had to sell the house and move into a flat, because it cost so much for him to go to Harvard. But that's a different story.
So how much is the Harvard kid? Where's he work?
Oh, okay. That's what I was getting at. He is now working on his doctorate in physics in Munich, Germany, at Max Planck Institute. That's why I started the story. Now, the interesting thing to that is we also have some German friends that live in Birmingham, and Olaf's parents live in Munich. Olaf, that's the German guy.
Snowman.
His father retired from Max Planck Institute in Munich, where Giacomo is now in school. So our Italian friends and our German friends, their spheres of influence overlap there. So that's why we know something about it. But Max Planck Institute, its major thing is in Germany, but they have institutes. He was in Grenoble, France, at Max Planck Institute there, using the collider that they have there. So he's working on his PhD in physics after having gotten his bachelor's in physics at Harvard. Okay, enough of that story. Let's take our break. When we come back, we'll do examples 8.1 and 8.2.
What time are we doing a lab today?
Okay. All right. Let's do the examples here that followed the quantum. I had to go back a couple slides to get enough space to write on. Okay. Now here's what we're using. Planck's law, basically. What is the energy? Okay. What is the energy? What symbol do we use to represent energy? Pretty simple.
Rho?
No. E. Energy. This is your energy, so this is what we're looking for. What is the energy of a photon of red light? If red light has a frequency, symbol for frequency? Just as easy. F, okay? The frequency of red light is 4.60 times 10 to the 14th hertz. And by the way, the symbol for hertz is Hz, named after Heinrich Hertz. That's why it's capitalized. And the actual units for that would be per second. But people got tired of saying per second, so they named it a hertz. Now, you might ask yourself, why didn't they put it just H, capital H for hertz? Well, they already had a unit for inductance named for that, and that was a Henry. I don't know if y'all run into, y'all deal with inductances much? Probably not, okay. I know you deal with ohms and volts and amps, but you probably don't deal that much with capacitances are measured in farads, which are named after Faraday, and inductance is named after Henry, and so that's capital H. So that's why we have to use Hz for hertz. Okay, so so what is the energy? What formula would we use? One we just had. There it is. Right? E is equal to HF. Can't get much simpler than that. So E is equal to HF, and H is Planck's constant. We'll go back and get that. 6.63 times 10 to the negative 34 joule seconds. So that's 6.63 times 10 to the negative 34 joule second times 4.60 times 10 to the 19th. A hertz, as I said, was a per second, 1 over second. Okay? So the second and the 1 over second cancels out. Does anyone have a calculator that will do scientific notation? Okay. I can't remember if the next test will have any of these on it. Not a bad idea to have a calculator that will do scientific notation. I don't remember that we have any, but I used to have a box of calculators. Either they died or they walked away, okay? Unfortunately, a lot of them walked away. So I don't have them anymore. I have one little calculator down in my office now, and it doesn't do scientific notation, so it was a freebie. Okay. Now, if your cell phones, if you got that, that'll be okay if you use that, but you need to know how to use them. I don't know, will cell phones do scientific notation? I would think they would, but I don't know for sure. They will? Okay. Huh?
You can download an app.
Okay, I'm sure you can. I'm certain of that. Okay, so here's what we do. 6.63. Now, if you got a calculator, I was going to ask if anyone did. Does anyone have a calculator? You?
He does. I gave it back to him.
Huh?
I said he does. I gave it back to him. He left me back.
Oh, I see. Okay. If it's a scientific calculator or better, then you'll have a key on there that is either the EE key or the EXP key. Can you find either one of those? EE or EXP? No? Take a look. Some calculators may have something else. Oh, there it is. It's right there. Times 10. So it's a different key. Some of the newer calculators will be times 10 to the x. So if you will, plug in 6.63, then press that key that says times 10 to the x. Now you have a little, you'll see the 6.63, and then you'll see a little block above it. And that block, okay, now your calculator probably has a minus sign with parentheses around it, right? It's not the subtraction key. Yeah, you see it? Press that key, that'll introduce the minus sign, and then press 3/4. Okay? Multiply that by your times sign, 4.6 times 10, and then that little thing do 19, 10 to the 19. Press your equal key, and you'll probably get something around 30 or so, 3, something like that. What you get as your answer?
3.0498 times 10.
Okay, let's call it 3.05 times 10 to the negative 14 power. And that would be joules. Not a whole lot of energy, but this is for one little atom. I mean, you're talking really small. 3.05 times 10 to the minus 14 joules. Wait, how'd they get minus 19 joules? Let's try that again. Is sure that's not a 19 rather than 14? Okay, look at your numbers. It's 6.63 times 10 to the minus 34 and 4.60 times 10 to the, maybe I put that down wrong. Oh, I'm sorry, that was 14. Sorry about that. That's 14, not 19. Okay, sorry about that. That was my bad. 10 to the 14th. And then that will make this 10 to the 19th, minus 19, right? Okay. Okay, minus 19 joules. Yeah. Very, very, very low energy. Okay? But it's a very small amount of thing you're dealing with. All right? We're going to do the same thing, but say what is the energy of a photon of violet light? This is the frequency for red light. The frequency for violet light, V, would be 7 times 7.30 times 10 to the 14th hertz. So basically all you do is change the numbers there. 7.30 and that will change these numbers to what? Okay, I'm guessing that's about 4.5 something, 4.8 something, something around in there. Did you do this one? Did you punch these in? No? Earth to Chris, come in please. Oh, never mind. Okay, all right. Yeah. If someone has a calculator, punch in 6.63 times 10 to the minus 34 times 7.30 times 10 to the 14, and what do you get?
6.6.
Huh? Yes. Okay, 7.30, yeah. Or 7.3 would be fine, times 10 to the 14. Four point. Okay, let's call it 4.90 times 10 to the minus 19 joule. Oh, they got 4.84. Okay, let's go back and check. 6.63 times 10 to the minus 34? Huh?
They just rounded it to the...
Oh, okay. I thought you said 4.899. Oh, I'm sorry. Okay, what did you say it was? Say it again.
4.839.
Oh, got it. I didn't hear the 3. So 4.84. Yeah, that's what they got to. Good deal. Okay. So let's now move to atomic spectra. Okay. Everything that produces any heat, any light, any radiation whatsoever, you can look at the components of that. Now, there's something called black body radiation. That just means something hot out there that's emitting. That's going to emit continuous radiation distribution. If you had the device that you're looking at, that you just see cloud of stuff out there. Okay? Now, that depends on the temperature of the radiating object. The hotter the temperature, the more radiation, and the wavelengths will be distributed. But it's a characteristic of solids, liquids, and very dense gases. Okay? You'll see these black body radiation. However, when you get very low density gases and very pure gases, you actually now don't see just a smear of radiation distribution. You get these individual line spectra. Okay? The emission at characteristic frequencies. Now, diffuse matter, like a light bulb, heating up that tungsten filament, it just incandescent. It produces, well, that's producing the diffuse matter in there is producing an incandescent gas. Okay? But if you had pure hydrogen in there, this is the Balmer series. Okay? Now, let's back up a little bit. Here is a light bulb. Okay? Probably an incandescent light bulb. Okay? Who developed this? Person? Thomas Edison. Okay? He went through multiple different metals, different materials, different things, different temperature, different conditions, different lots of things, until he came to something that glowed with a light fairly close to what we get from sunlight. Not exactly. Most incandescent light bulbs are a bit on the yellow side. Okay? But if you send this through a slit, okay, here, so you're only giving a little bit of light through here, go it into a prism, the prism is going to split that because of what we call diffraction. It splits it once as it goes in here, and again when it comes out here, spreads it out some, and you get a little bit of red, orange, yellow, green, blue. Somewhere in there you could call it indigo, and then violet. Low energy, high energy. Okay? That's the spectrum of light. If that was pure sunlight, these are probably more evenly spaced. I don't think this is precise. I think for an incandescent bulb, probably the yellow is thicker and the violet is less. Okay? But anyway, that's what you get, a diffuse spectrum. Okay? Anything that's producing light. If you had things like a laser, which is one material doing, then you probably get something a bit more like a line spectrum. Okay? Now, this is a tube, and let's see, this may be hydrogen. I don't know for sure that it is. I think they were hinting that it would be. So you've got one single gas in here that is emitting, okay? That you have mercury vapor, so you got a variety of things in there. One single gas, it splits, and now you get line spectra. They're not running together, that's individual lines. A red line, a blue line, a violet line, and then you probably can't even see that. It's probably ultraviolet or something like that. Why they show it, I don't know. But you get individual lines, okay? That would be if you had a pure gas, especially a low-density gas like hydrogen or something like that, you can get just the individual lines rather than a diffuse spread like you got with the incandescent bulb. Okay? Now, there was Danish physicist, Niels Bohr, who came up with a theory, and boy, did it work well on hydrogen. Okay? Didn't work anywhere else very well, but it worked great on hydrogen. His three rules were, electrons only exist in certain allowed orbits. Okay, I've already been referring to that before. Within an orbit, the electron does not radiate. So if that electron, even though it's moving in a circular path, it's not accelerating. It's fixed and it does not radiate. Radiation is emitted or absorbed only when it changes its orbits. And that's what I was telling you, this happens here. When that ionized gas is flying down there, it makes the electrons in that powder jump up a level, and then when it goes past, they fall back down because it can't stay up there. But when it falls back down, it emits light at a certain spectrum. So that's what Bohr was saying. Radiation is only emitted or absorbed when it changes its energy level. Okay? And when it does, like it has been jumped up there for some reason, like a ionization or something has happened, but then when that passes, it falls back down, then it gives off a photon of a specific frequency. And that's why you get those line spectra, like we saw. Okay? So here is the quantum theory of the atom. The lowest energy state is this one, the ground level. Okay? That's as low as you can go. Now, in the old days, before quantum mechanics, they thought you could get to a zero energy level. No, well, they thought you couldn't get there because there they said all motion would stop. In quantum mechanics, they say, no, you never, all energy stops. You can get to a lowest level, but it still has some energy. That's one difference, okay? Now, these are showing the line spectra that you get from hydrogen, okay? If it's jumped up 4 levels above, it's going to come back to 2, by the way, and we're not going to get into why. It falls down 4 levels, it gives you violet light. 3 levels, it's a different violet light. 2 levels is a blue-green light, 1 level is a red light. More energy here, less there, the least there. These are the individual Balmer lines that you see with hydrogen gas, okay? The lowest energy is the ground state. The higher states are excited states. When they fall down off of those excited states, they give off photons of light. And they will be different colors, violet, blue, green, or red. The photon energy equals the difference in those state energies, okay? Now, what we're dealing with there, remember, you have the nucleus, and then you have these levels of energy that things can be excited to or not, okay? And if they do get excited to a higher energy and fall back down, they're going to give off these specific line of frequency. So the photon energy that is given off here, these are your frequencies. For violet is this one, that one, blue-green is that one, and red is this one. So that's the difference in energy level from up here to down here, from here to here. So that's how all this works out together. That's where you get your line spectra. Okay? This was Bohr's model. Works really, really well for hydrogen. But remember, hydrogen, a single proton, a single electron. As long as when you get up to helium, which has 2 protons, 2 electrons, everything gets all messed up. So his model didn't work anymore. But this was the beginning of basically quantum mechanics. The Bohr theory only modeled the line spectrum of hydrogen, but it did it very, very well. Further experiments established another problem. Now here's the thing, folks. Remember I was telling you historically, physicists thought they had it all nailed down, just had to finish up a few things. Then they discovered quantum mechanics. Everything was up in the air. And the more things they found out about it, the more rat's nests appeared. More questions came up. So further experiments established, guess what? Light is not just energy. Light also has particle nature, a photon. So now, before they were dealing with just with frequencies, can't just deal with frequency anymore. You have to take into account the wave nature, which is frequency, but also the particle nature, photons. And boy, things really get complicated. Okay? Young, and this is another guy you could look into. His last name was Young. Let me see if I can find the first name for him. Okay? And they don't give the first name for Balmer. Oh, yes, here it is. A Swiss mathematician, mathematics teacher, okay, named J.J. Balmer was studying the regularity of spacing of the hydrogen line spectra, and he developed this table that we just saw here. And he came up with the concept of how that could all fit together using mathematical analysis. That became known as the Balmer series. Unfortunately, it only works for hydrogen. Okay. So let's do, while we're here, I didn't realize we had one. Yuck. Yeah, here's a place. Ooh, I'm going the wrong way. Good deal. Thank you. You ready for the next one? Okay. If you'd rather go to another room if this is too noisy.
I might, but I think there's people in that other room.
What's that?
I think there's people in that room over there.
Okay, well, I'm sure somewhere down the hall we can find something. Let's see, test 2. Test 2, test 2, test 2. Test 2, test 2, test 2. And test 2. Here we go.
Thank you.
All right. So let's do, where was I? Here we go. Let's do example 8.3. Calculate the wavelength of the violet light where n is equal to 6, okay, and the hydrogen line spectra according to Balmer's equation. Well, Balmer's equation, they didn't put it on the slide, but let me write it down for you. 1 over lambda, okay, that's a Greek letter lambda, it stands for wavelength, okay, is equal to R. Now that R, do they tell you here? Yeah. All right. You have to go to the front inside cover of your book. I mean, they give you the number, but the R here is under physical constants. Goodness gracious, I don't see it here. Oh, there it is. Where all they say, they don't give you the name of it. I wish they did. It's R is a constant of 1.097 times 10 to the 7th, and that's per meter. That's all it is, per meter. It's a constant, okay? And the rest of the formula is 1 over 2 squared because you're going to the second level minus 1 over n squared. And here we're going to n equals 6. Okay? So all they're wanting you to do is plug in and see what you get. So we're looking for lambda. It said, what is the wavelength? That's lambda. So 1 over lambda is equal to, r is 1.097 times 10 to the 7th. And that is in per meter, 1 over meter. And then you multiply by 1 over 4 minus, and here n is equal to 6. That's supposed to be an n. It looks like an h. Okay? And that would be 1 over 36. Because 6 squared is 36. So it would be 1.097 times 10 to the 7th per meter times, and what's the least common denominator between 4 and 36? Say again?
36.
36. How many 36 is 4? 9 36 minus 1 36 is 8 36. Okay. All right. So what you do, you can reduce that, and that would be 2/9. Okay. So you can multiply that number, r, by 2, divide by 9, and what does that give you? 1.097 times 10 to the 10 to the 7th, multiply by 2, divide by 9, what do you get? Someone with a calculator. Help me, help me. Anyone got a calculator?
What's up? I got a calculator.
Okay. 1.097 times 10 to the 7th. You know how to put that on the calculator? Scientific notation?
10 to the 7?
Yeah. Multiply by 2, divide by 9.
I don't think it's right.
What do you get?
10,700,000.
Okay, that may be right. Say it again.
10 million.
10 million?
Thousand.
10,700,000?
Yeah, I don't think that's right.
Yeah, I don't think it doesn't seem right either.
1.097.
Times 10 to the 7th. That would be 10 million. 970,000. And you're multiplying that by 2 and dividing by 9. Anyone got it?
I don't have it. It's not working on this.
Okay.
You can do scientific notation with an iPhone. I
Yeah.
just don't remember how to do it.
You want me to look and see if I can figure it?
Come over there. You're good. On this side, 1.097. This got x2, x3, xy, ex, and
And then for second.
well, there you go. That seems a little more.
Okay. But all we that didn't seem right. Okay, let's start over. Clear. Yeah.
When did I have a scientific calculator?
1 point,
Maybe. It's just smart.
1.097
Sunshine.
EE 7
John Brown.
times,
Typical name.
yeah, that's it, times 2 divided by.
So that's 2,437,777.7.
Okay.
How much?
All right. Now, with that number still up there,
777.
that number up there. Okay, wait. That number up there, we want to reciprocate that. So
What's that mean?
that means you 1 over. There's 1 over x. So press that. That's what you get. Count the numbers here. 1, 2, 3, 4, 5, 6, 7 after the 4. 4.1, 1, right? 4.11 times 10 to the, how many we count? Minus 7?
6.
Minus 6. No, it was minus 7. Because you go one past, no, number of zero,
Oh.
one past, yeah. Okay, and that would be meters. Okay, that would be the wavelength of that thing. Now that's in meters. If you go to millimeters, it's even smaller unit. So you would increase that to 4.11 times 10 to the minus 4th millimeters. Okay, if you wanted to go that way. But that's exactly what they get in the book. 4.11 times 10 to the minus 7 meters. Okay? Now, we should have done that back with Balmer's. Now we're moving to Bohr's theory. We've already done that. Actually, they got this a little bit out of order. Okay? So now we're moving to quantum mechanics here. No, okay. Before we get to quantum mechanics, let's do example 8.4. All right, let's clear this. Is it time? 5:45 is when we do it, and we're not quite there yet. Okay? You're wanting to go, huh? Okay. I'm sorry, I didn't say that. Okay. All right. 8.4. An electron in a hydrogen atom jumps from the excited energy level n equal 4, falls down to n equal 2. What is the frequency of the emitted photon? Okay, so now we're looking for frequency. Okay? Well, we'll use the other equation that we were given, HF, and this was on a slide. Let's see if I can find it. There, nope. I thought it was on a slide. Here it is. HF is equal to EH minus EL. Higher level minus lower level. Okay? So HF is equal to EH minus EL. Okay? So what we do here is H, which is Planck's constant, which was Planck's constant was 6.63 times 10 to the minus 34, and that was joule seconds. My writing stinks. Joule seconds times F. That's what we're looking for. What is the frequency? Is equal to EH minus EL. Okay? What you have to do is go to, let's see if I can remember which direction it was. Here we go. Here was 4, here was 2. 4's energy level was 1.36 times 10 to the minus 19, and 2 was 5.44 times 10 to the minus 19. Now those are all negative, so let's go back. This makes it sort of hard to do. I'm going to just pull it from the book. Negative 1.36 times 10 to the minus 19, right? Yep. Minus 19 joules minus a negative 5.44 times 10 to the minus 19 joules. Okay. Now, if you got a calculator, subtract those two. It's not a hard subtraction. This stays negative. That goes to positive. So you subtract this from that because the minus 19 is the same. And that would be 4.08 times 10 to the minus 19 joules. So that difference is 4.08 times 10 to the minus 19 joules. That's the difference in that. divide that by Planck's constant, 6.63 times 10 to the minus 34, and this will be joules second. Okay, joules cancel out, and this gives you a frequency in per seconds. Someone with a calculator, punch that in. Or if you got a cell phone, we know they'll work. So 4.08 times 10 to the minus 19.
08 times 10 to the negative
19 divided by 6.63 times 10 to the negative 34. Incredibly small numbers. What do you get? Anyone got it? It looks like about a 0.6 maybe, or 6 point something.
6.63.
6.63. Oh, no, that's the bottom number. Okay.
Negative 34?
Yeah, that's the bottom number. 6.16. Is that what you said? What did you say? 6.15?
Yes.
Okay. Times 10 to the 14th hertz, or per second. And let's see how the book did. 6.15 times 10 to the 14th hertz. Perfect. All right. So you see how to use these formulas. Not that you'll really have much need for them. I don't think there'll be any like this on the test, but this is how they put it together. All right, so let's look at quantum mechanics. This is section 8.3 in the text. Okay? Bohr's theory only modeled the line spectra of hydrogen. Way too complicated to get even helium or anything more. Further experiments established the wave-particle duality of light and matter, which was another whole brand new concept here. And oh, that's what we were looking before. Who in the world was young here? I don't see his name listed. And by the way, read the text and you'll find just tons and tons of people are mentioned here. Let me just hit a few of them for you. I don't see Young here. I've heard it before, but I can't remember which one he was. But looking at the text, you'll see that a German physicist, A. Sommerfeld, tried to modify Bohr's model by adding elliptical orbits in addition to Bohr's circular orbits. And that was where we got into the last thing. Then under 8.3 quantum mechanics, you'll see another name shows up. Good old Einstein, okay? And Einstein applied Planck's quantum concept to a photon with a relationship found at 8.1, E is equal to HV, which is H alpha, which is frequency. E is the energy of a photon particle. Alpha is the frequency associated with the matter, and H is Planck's constant. Then, okay, and now we're going to get into this concept of matter waves. You have waves, which would be light. Matter would be more like the photons. And we run into a guy named Louis de Broglie, okay? He's a French physicist, though de Broglie doesn't sound all that, yeah, I guess it is. I remember taking quantum mechanics under an Irish professor at Georgia Tech, and I could hardly understand the guy. His brogue was so thin, and it was de Broglie. I mean, he just rolled that R like crazy. This is in 1923. He postulated that matter has waves as well as radiation having waves. No one had thought of that kind of thing before. Now, what you're dealing with is very tiny, tiny particles of matter, like electrons, like, other very, very small things. A baseball? No, you're not going to be able to detect the wavelength of that. The wavelength of these tiny particles was related to the momentum, which remember was mass times velocity. The matter waves and atoms are standing waves. Okay? Now that is sort of a new concept here. And de Broglie was largely responsible for this. And this was the modification that we had, that the particle wavelength, these are particle waves, so a particle wavelength, lambda, was h, which is good old Planck's constant, showing up again, over the momentum, mass times the velocity. And by the way, masses we're talking about are incredibly tiny masses. These have to be really tiny particles, and they could be moving at very, very, very high speeds. Couldn't be the speed of light. Why not? Nothing, no particle can travel at the speed of light. Radiation can travel at the speed of light because it doesn't have any mass. Mass can't. Okay. Second.
Chris's race car again.
Who's race car?
Chris.
Oh, I see. Okay. Close anyway. Really close. Okay.
Yeah, it's quite turbo.
Now here's what de Broglie found. Okay?
It's all about the supercharged.
Okay.
Not turbo.
All right.
Oh, shit.
All right. Okay. That's actually way more down to earth than this is. What we had, remember the orbit that Bohr was modeling was a circular orbit. Someone came up with the idea, what if they're really not circular orbits? What if they're actually waves following around the orbit?
Dr. Feller, it is 5:45.
It is 5:45, but let me finish this slide,
Yes, sir.
and I will call roll. Okay? So, in order for this, de Broglie's particle waves to work here, you have to have a complete circuit here. You can't have something that disconnects like this. That's a misfit. This is what they mean by a standing wave. I don't know if you've been to McWane Center and seen their wave generator, and sometimes it's all chaotic, but if you hit a certain frequency and the light is flashing on it, it looks like perfect sine waves. Okay? That's what you need here. You need a certain specific frequency here, and that's what gives that particle, that electron, actually is following a wave pattern rather than just going around in a circular orbit. And as long as it does that, it's not radiating. When it jumps up to the next level or falls back down, then it either absorbs or emits radiation. So that's what they mean by standing wave. All right, we'll pick up, we'll do example 8.5 after I call roll again. If I can find my pen. Oh, there it is. Okay.
What about that test though?
Rachel is still here. John is still here. Chris Davis is still here. Yale is still here. Thomas is kind of here. Okay. Hunter is mostly here.
So you can give that test.
Justin is here. Eric is here. Ashton's still here.
Haven't figured that one out.
Andrew's still here. Chris is still here. Did you leave just briefly and the class didn't meet or something? Oh, never mind. Okay.
Civic in the Kia.
Okay, David.
Sorry, brother.
Did we lose David?
He's not in.
Huh?
His stuff's here, but he's not in.
Okay, well, we'll hold off on him then.
There he is, right there.
No, it's not. That's okay. Chelsea hasn't made it in yet. Alex, is he still in the back? Yeah, there you are.
Alex.
Don't know what he's doing back there, but he's still back there. Okay.
Hello.
USA is here. Melva's here.
It feels like he learned.
Samuel's even here most of the time.
Yeah.
Angel's here. Lisa, we think, is probably gone, and Scotty, of course, too. Adam's still here.
So that's just it.
Ashland's here.
Oh.
Kedrick, we haven't seen this evening. And Jared, we still got. All right. Haven't lost anybody yet.
Scotty's here.
All right.
Scotty said about to take
Okay.
a walk.
All right. Before we get into wave mechanics, let's do 2 more examples. All right. We'll do them here. What is the wavelength? So again, we're looking for lambda associated with a 0.150 kilogram baseball. What's that a measure of? 0.150 kilogram baseball.
John Brown said May.
Said what?
Man.
Mass, yes. Okay. That's your mass. It has a velocity of 50 meters per second. They already told you what that was. That was velocity. Okay? We will use the Broglie's relationship. And that relationship was lambda is equal to H over mv. And there's Chelsea. Is what? Is what? Well,
Come in.
I'm in here. Okay.
I'm in here. He's in the room. Come in, boy.
Don't be scared, boy.
Okay. Chelsea made it in.
What are you doing?
Did you finish?
That's what she does.
Good deal.
Walk
We'll
right
see you
in.
Tuesday. Okay.
You don't come to class.
All right. Still haven't seen David though, right? Okay.
You came here and dropped the stuff off.
All right.
And probably too.
All right. So H was, anyone remember what H is?
What is that?
Planck's constant. And what was Planck's constant? 6.63 times 10 to the minus 34 joule seconds, divided by the mass of 0.150 kilograms times velocity, which is 50.0 meters per second. Okay. It doesn't quite look like units are working out right, but I guess they are. Yeah, they do. All right. Does anyone remember what a joule is?
It's a measure of
Energy. We got that. But what are the fundamental units for joule?
Justin, how do you remember that?
Well, energy is the same as work, right? Energy is the same as work. Work is force times the distance, right? Well, force is mass times acceleration. So that would be kilogram meter per second squared times meter. Okay? Well, this per second squared cancels out 1 second there. So you're left with per second. The per seconds cancel out here. One of the meters cancels out here. And the kilograms cancel out there. So all you're left with is meters. That's a good thing for lambda to be measured with. All right, let's see what kind of number we get. Anyone got a calculator? 6.63 times 10 to the negative 34. Divide that first by 0.15, and then divide it one more time by 50.
Times 10 to the negative 34th.
Yeah, the top number is times 10 to the
times
negative
1,000.
34. So again? and then divide it by 0.15 and divide again by 50. Or you could multiply those two together if you wanted to. It doesn't matter. It's easier to just divide like that.
2.15?
2.15 you said?
No, you said divided by what?
By 0.15. Take this number, 6.63 times 10 to the minus 34, divide it by 0.15, and then divide that answer by 50. Anyone got it? Does anyone have it?
What's that?
6.63 times 10 to the negative 34 divided by the product of 0.15 times 50. If you wanted to multiply that out, that's 7.5. So divide that top number by 7.5, and what do you get?
6.63.
Nope. So, you're put 6.63 times 10 to the minus 34 divided by 7.5. 8.84 times 10 to the negative 35th meters. Okay? Guess what, folks? You're not going to measure the wavelength of a baseball going at 50 meters per second. Too massive, really not very fast at all, but way too massive. It's going to be such a small wavelength, you will never, ever, ever detect it, no matter what kind of equipment you have. Okay? However, let's do another one. What is the wavelength associated with an electron with a velocity of 6 times 10 to the 6? So now we're looking, this is a baseball, this is an electron. That would be your H, which is 6.63 times 10 to the minus 34, and we'll put all those units down again. Kilogram, meter squared, per second squared, times second. So you lose one of the seconds. Divide that by, this time you got an electron. We got to look for the mass of an electron. Go to the front inside table of your text. Electron rest mass is 9.11 times 10 to the negative 31 kilograms. 9.11 times 10 to the minus 31 kilograms. And it's traveling at 6 times 10 to the third meters per second. 6.00 times 10 to the 6. I said third, it's 6 meters per second. By the way, that's 6 million meters a second. That's moving, folks.
That's a
really fast. Oh, almost. Okay. All right.
Thomas is Honda.
Okay.
Why don't you get from the
So if you got your calculator, here's the best way to do this. Rather than multiplying these two first, you could do that, but do 6.63 times 10 to the minus 34. Are you listening? Divide by 9.11 times 10 to the minus 31, and then divide that answer by 6 times 10 to the 6. Excuse me. Have you done it? Anyone plug in the numbers? Just do this, divided by that, and that answer you get there, divided by that.
That's 9.11 or 9.16?
9.11 times 10 to the negative 31. Let's listen down again. That's the rest mass of an electron.
Negative 31.
Negative 31, right. And then divide whatever answer you get from that by 6 times 10 to the 6th.
It's 6 point.
You don't have to put the 0.00, but you can if you want to. So the kilograms go out, 1 meter goes out, the per second goes out, and you're left with meters. So what's the wavelength of that electron? Anyone got it?
John Brown.
I'm working on it.
times 10 to the negative 34. $1.21 times 10 to the negative 4.
Perfect. 1.21 times 10 to the what?
Negative 4.
Negative 4?
That's what the calculator has.
I think you left off the 10 to the 6 before. It's negative 10. That last 6 was 10 to the 6 times 10 to the 6th.
Oh, okay.
Right there. Yeah.
Okay.
So it gives you times 10 to the 10th meters. Guess what, team? That's a frequency. I mean, that's a wavelength that we can measure. 10 to the negative 35th, no way in the world. 10 to the negative 10, still a small number, but that can be measured. That's a matter wave. Okay? Now, it's nowhere near as big as a frequency wave, like actually electromagnetic radiation, but it's still a matter wave. Baseball, nah. Has one, but it's not measurable. Okay. So, all right.
Those problems.
All right. Now, we're moving to wave mechanics. All right. Believe it or not, there's a purpose for all this madness. Okay? Here's another name in case you needed somebody else you might consider. Excuse me. Wave mechanics were developed by Edwin Schrödinger. By the way, he came up with a pretty famous equation called Schrödinger's equation. Okay? He treats the atoms as three-dimensional systems of waves. We think of waves as being two-dimensional. He had a three-dimensional system of waves. The mathematics of that, pretty hairy. Okay? It contains successful ideas of the Bohr model and really, really a lot more. His wave mechanics really covered a lot. Describes a hydrogen atom and many electron atoms. In other words, beyond one electron, multiple electron atoms. It forms our fundamental understanding of chemistry. That's why we've been doing this. Schrödinger's wave equation. Okay? His wave mechanics. And it's one hairy-looking equation, too. We're not going to go into it. So, here's what you get out of it. The quantum mechanics model gives you this. We're going to talk about 4 different quantum numbers. The quantum numbers specify the electronic quantum states. Okay? I know it probably sounds like a lot of blah, blah, blah now, but it really gets to be what you're dealing with. The visualization here is you now have wave functions and probability distributions rather than, here's the point. You can't say the electron is there, okay? You can never say that. What you can have to wind up saying is the 90% probability is somewhere in there, okay? You just eliminated the 10% that's out here, 90% chance it's somewhere in there. That's the best you can do. In fact, there was another guy named Heisenberg. Anyone ever heard of that?
Yes.
What? Huh? Not the blimp. Yeah.
I know it's not Hindenburg, but did he have to do anything with air stuff? Airplanes?
No, you're thinking Hindenburg. Okay? That's the blimp. Okay? Heisenberg basically came up with this postulate. If you can locate an object, a quantum mechanic object, there's no way you can ever tell its velocity. If you tell its velocity, there's no way you can ever determine its location. It's called the Heisenberg uncertainty principle. You can know one thing, but you can't know them both. Okay?
If you can locate it, that means it's not going fast.
No way you can measure its velocity.
Okay.
Okay? Or if you know its velocity, there's no way you know where it is. That's the Heisenberg uncertainty. That's in a nutshell. It's a lot more complicated than that, not nearly that simplistic, but it's like that. Okay, yeah.
Thanks.
Okay, that's where.
I know.
Okay.
Stop.
Now, so we're visualizing things with wave functions and probability distributions, which the mathematics of that are really pretty horrendous. The electrons are not localized, they're delocalized. They're somewhere in that mess, okay? But that's all you can say about it, okay? Now, you have these 4 quantum numbers. The first one is called the principal quantum number. We also usually call that its energy level. And that has to do with the average distance from the nucleus. Remember, we don't know where the electron is, but we know on average about how far it is from the nucleus. That's its first quantum level number, and that's called N. Okay? And this is a pretty simple thing to deal with. Okay? In fact, if you look at your periodic table, I'm sort of jumping ahead, but hopefully this will help it make more sense to you. Guess what? There's only 2 elements on N equal 1. Hydrogen and helium. That's all, folks. At the first energy level, only 2 elements have only 1 energy level. Hydrogen and helium. Okay? Now, every other one in here has electrons on that first energy level, but then they have electrons beyond that. Hydrogen and helium, they only have that 1 level, unless they get excited and they jump up. The second of our quantum numbers is L, and that's called the angular momentum quantum number. It's sort of a spatial distribution. The first is an energy level. The second is a spatial distribution within the energy level. Now, if you're in level 1, N equal 1, the spatial, you only have S angular quantum numbers. Okay? Only S. For N equal 1, you only have S. For N equal 2, you have S and P. Okay? For N equal 3, you have S, P's, and D's. For N equal 4, you have S, P's, D's, and F's. And for N equal 5, you just keep on going up. Okay? So that's your spatial distribution. On average, how far it is from the nucleus, that's your energy level. How is it distributed in that energy level? That's your S, P, D, and F. Those are your angular momentum quantum numbers. Okay. The third one, the magnetic quantum number. It doesn't have a letter. We just call it the magnetic quantum number. It's the spatial orientation of the orbit. What in the world does that mean? The spatial orientation of the orbit. We'll get to that a little bit later, so hang on to that. And number 4 is the spin quantum number. That I can tell you. It's either spin up or spin down. Only 2 possibilities there. And we usually say plus 1/2 or down or minus 1/2. However you want to do that. Okay. So, within any energy level, you always have an S. The S is basically, like it said, your spatial distribution is kind of in the sphere. So you can think of that as being what S stands for. That's probably not what it stands for, but you can call it that. Okay? The P orbitals, you have 3 possibilities. Each one is along an axis. This is centered at the origin. There's only 1 S orbital. The P's, you got 3 of those. You can be along the X axis, the Y axis, or the Z axis. So you can have these barbells along any axis. Okay? Let's see if they go any further than that. Okay, yeah, here it is. These are the 3 orbitals. Along the x-axis, along the, which is at the y-axis, and then along the z-axis. They oriented strangely. Those are your 3 possible p orbitals within it, and that would only be for n equal 2, 3, 4, or 5 that you could have a p. Okay? Now, and this then lends itself to the magnetic quantum number. Is it this way? Is it that way? Or is it that way? In other words, what is your spatial orientation of the orbit? Okay? And then the fourth one, spin up or spin down. Electron spin orientation. Okay, let's go back to the S. The S can only have 2 electrons in it. One spin up and one spin down. Each p orbital can have 2 electrons, one up and one down, but you can have 3 different orientations. That's your magnetic quantum number. You can have 2 in here, 2 in there, and 2 in there. Okay? That's your spin quantum number. Okay? Now, and this shows that spin up or spin down. Sometimes they use plus or minus a half or other things to represent that. Doesn't really matter. It's spin up or spin down. All right. Now, let's sort of put all those things together. When you're in your first energy level, you can only have one sublevel. Okay? That's the angular momentum quantum number, S. And S has only 2 electrons, spin up or spin down. When you're in the second energy level, you can have 2 S electrons, and you can have 3 P electrons. Okay? The P is the angular momentum quantum number, and then the orientation is your magnetic quantum number, and then the spin is up or down, so that gives you 2, the P level can have 3 orientations, 2 electrons in each orientation. So when you're in n equal 2, the maximum number of electrons you can have is 8. Period. N equal 1, all you can have is 2. 1 or 2. N equal 2, you can have 1 through 8. For n equal 3, your S can only have 2, your P's can only have 6. Now, it's really hard to illustrate the D's. Okay? The D's have 5 different orientations. So let's look at our orientations here. Your magnetic quantum number. 1, 1 and 3, 1, 3, and 5. Guess what this one will be? 1, 3, 5, and 7. These increase by 2s each one. Okay? But every orientation can have 2 electrons in it. So if your D has up to 5, it can hold up to 10 electrons. You had on the third level, you can have 2 S electrons, 6 P electrons, and 10 D electrons. That gets you up to 18. Okay? For n equal 4, you can have 2 S electrons, 6 P electrons, 10 D electrons. Then your F can have 7 orientations. 1, 3, 5, and 7. 7 times 2 is 14 electrons. You add those together, 14 plus 18 is 32. You can get up to 32 electrons in n equal 4. Okay. Those are your 4 basic quantum numbers. N, main energy level, how far you are from the nucleus. Your second is your angular momentum quantum numbers, represented not by numbers but by letters, S, P, D, F. You can't keep going. Usually you don't. Okay? And then the spatial distribution within that, you have 1 orientation for S, 3 orientations for P, 5 orientations for D, 7 orientations for F. Each one of those orientations can have 2 electrons by spin, 1 spin up, 1 down. So you double each of those, and that's where you get your 14, 10, 6, and 2. Now, let me go on and show it to you. Okay, I don't want to wait until they do. Take a look at your periodic table. First level, 2 electrons is all you have. S only has 1 orientation, 2 electrons of that, hydrogen, helium. Go to the second energy level. It can have an S, there it is, lithium and beryllium. Okay, that's all it can have for S. Then go to P, 3 orientations, 2 electrons per orientation. There's boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay? Now, we'll get to this a little bit later. We don't fill our D's yet. We go back to the third and do S and P again. But once we do that, then we do our 10 here. Remember, this is 3 times 2 is 6, 5 times 2 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why the periodic table looks the way it does. And guess what? Down here, you interject 2 more rows in here. That is, let's go back here. Those are your F's, and the F has 7 orientations, 2 electrons per orientation. That's 14 more. Look what your last 2 tables are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these quantum numbers is what makes your periodic table look the way it does. The S's have 2 each. These are always your S electrons here. Your P's have 6 electrons maximum each. That's why you have these groups of 6's here. Your D's have up to 10 electrons. That's why you have the 10 in here. And your F's have 14, up to 14 electrons. And that's where you get these 14 out here. These fill in the gap here. This table goes up here, that goes down there. That's why the number's right there. You don't have just long enough paper to do it all out. Okay. So, the electron configuration, the arrangement of electrons into the atomic orbitals. That's what you're doing. You're filling these shells as you get to them. The first one is called the principal quantum number. That's N. 1, 2, 3, 4, 5, 6, 7. Okay? Angular momentum quantum numbers. They're not they're numbers, they're letters. That's S, P, D, and F. You can't have more, but our periodic table runs out of elements before you fill F. Okay? And then the magnetic quantum numbers is the orientations within those shells. So S can have only 1 orientation. P can have 3 orientations. D can have 5 orientations, however they go. And F can have 7 orientations, however those go. And then finally your spin up or spin down in each orientation. That's why S has 2. Principal quantum number 1, angular momentum quantum number S, 2, 1 orientation, 1 magnetic quantum number, and 2 electrons. It can have 2. Principal 2, S, 1 orientation, 2. Principal 2, angular momentum can be P. 3 orientations, up to 2 electrons each, 6 more. So you just keep adding that way. Okay? This collection of those 4 quantum numbers specifies every atom's quantum state. And that's what puts them in where it falls in the periodic table. Now, another guy, an Italian scientist named Pauli. Okay? By the way, before I get into that too deeply, at the top of page 217, Atomic Research, that talks about some of these people. Again, J.J. Thompson, Robert Millikan, Ernest Rutherford, Niels Bohr, Erwin Schrödinger. I keep saying Edwin. Erwin Schrödinger. Okay? Each of them proposed a next model. And by the way, there on page 217, you'll see the Heisenberg uncertainty principle, what I was mentioned before. Okay? And there they do have pictures of the d orbitals. You see the s orbital, 1 orientation. P orbitals can have up to 3 different orientations, 2 electrons per orientation. That gives you 6. The d, if you can figure that one out, it has 5 orientations, each holding 2 electrons for 10. And then, I can't even imagine what the F looks like with 7 orientations, up to 14 electrons. Okay. Here we have Pauli exclusion. I was trying to find that. Yeah, there it is. This is at the bottom of page 218, left-hand column. Electron spin is an important property of electrons that helps determine the electronic structure of the atom. As it turns out, two electrons spinning in opposite directions is called an electron pair. They can occupy the same orbital. That was summarized by Wolfgang Pauli. I said he was Italian. I think he must have been originally from Italy, but his family was, but he was Austrian. His summary now known as the Pauli exclusion principle. Okay? Each electron has one unique set of quantum numbers. Pick any electron out there in whichever atom you have, and it has one unique set. N may be 1 through 4, 1 through 7, something like that. Your angular momentum is either going to be an S, a P, a D, or an F. That's all we go to. You could have higher, but that's all we use. And then your orientation, or either for S is going to be 1, D is going to be 3, P is going to be 3, D is going to be 5, and F is going to be up to 7, and then the spin up or down. So each one will have a unique, every electron has a unique set of quantum numbers. Nothing is repeated. The chemical properties are determined by that electronic structure. How active or inactive a chemical is, an atom is, an element is, will depend on that electronic structure. And that's what chemistry is based on. Even though we knew some stuff about chemistry before, we didn't know why until they figured all this out. Okay? All right. Now, yeah, what I was just trying to sort of puzzle through is where would be a good place to stop tonight. Okay, wait. Okay, wait. Here's the situation. What's that? I can't hear you. I can't leave before 8. We have to stay what our locator card says. I'm going to be here till 8. What I'm thinking is, though, is that your lab that we're going to do, a little bit of what we talked about so far is going to be on the lab. But the hardest part of what's going to be on the lab is what we're going to do next, writing electron configurations. So since we can't do the lab tonight, or I don't think we'll have time to do the lab tonight, what we'll do on Tuesday is finish the chapter, which is basically 8.4, 8.5, and 8.6. I think that pretty much sums it up, okay? Now, that sounds like just half the lab. Actually, the 8.1, 2, and 3 were the big halves. These are much shorter sections here, okay? So that's what we'll do. We'll just go on and pause here, okay? So next time on Tuesday, starting at 3:15, we'll pick up with 8.4, and we'll do this writing electron configurations. Now, it's based on what we've done tonight. So I'm not going to have time to go back and go through all this tonight that we've done tonight. You're going to have to remember that. So we're going to base on that, and the lab is going to be what we did earlier tonight, plus what we're going to do next time. I don't think it's going to take us to cover this much more than half an hour, maybe 45 minutes, maybe an hour. Depends on how fast we go. The lab itself, I don't think will take you more than another hour, maybe an hour and a half. I don't think it'll take anyone 2 hours to do, though it's sort of involved, okay? So that means we'll have some time left over at the end. Now, here's what I'm trying to piece through. I want to give you enough time next time to do the lecture, do the lab, and if you want to, do the test. But if I leave too much to be done in lecture and then the lab, you may not have time to do the test. So that's what I'm trying to time it out right for you. Okay? I think we can probably squeeze it all in if you want to do that next time. Are some of you planning to take both the Chapter 8 test and the final next time? I thought a good number of you were.
Yeah.
Okay. That means you better read what we're going to be talking about, because you're not going to have time to go home and study it, because you're going to have the test right after we do it.
Tell you what, I'll know every bit.
Okay? Yeah. Okay. Now,
Well,
here is the other question.
This much opposite.
Okay? Especially you guys in auto mechanics. Okay? Are y'all going to have time to eat lunch before class, or are some of you going to be dragging in way after?
I'll get here
3:15.
right on time.
Okay. Here's what.
Dr. Phillips, you know
Okay.
we're here for
Here's why I'm going to ask this. Okay. What we can do, since I'm guessing we'll have pretty close to a full house on Tuesday, if y'all can get here on time, I can try to have pizza here. So y'all don't have to go somewhere to eat lunch.
Yeah, I agree.
Will that work for you?
That works perfectly.
Okay. All right.
So 3:15, you'll have pizza here.
I'll have pizza here.
Oh, you got
Is that all right?
No, she doesn't get pizza. She has to come in at 5:45. She can't
Okay.
come on time for the one pizza.
Okay. Here's the deal then, folks. How many pieces do you think you'll need to consume? Look at how big a group we got and how big of eaters you are. What would be your guess on pizza? Okay, we're eating Little Caesars. That's close. Sorry about
9
that.
or 10 pizzas.
9 or 10?
9 or 10 pizzas.
1 4 times 10 to the
I can eat
10th.
half a pizza.
Okay, but that doesn't mean.
Okay.
That's
What's
what I'm
that?
saying. I'm talking about like 10 pieces.
One or two.
How about we take a vote of like how many pizzas each person would eat?
Okay, let's give a guess on that.
Don't be greedy, just get two.
Let's
Okay.
say two.
I mean,
Is it
most
two?
guys.
two
I
slices.
don't want to limit you to
I'd
two.
be happy if I had 3.
3?
2, 3, 4 slices.
I'm gonna say two per person.
Huh?
If
I'm gonna say two per
I
person.
eat
2
more
to
too,
3 slices per person.
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 people
If
here.
there's going to be food,
You gotta count
Scotty in. Count David in.
David will be here. 21.
Hey, you gonna count Scotty in?
No, I won't count.
You won't count Scotty in?
26.
I think four.
Probably.
4 pizza?
Yeah, four.
You think 4 will do? Okay, here I have. Okay.
Let's go with the original two.
Okay. Will 4 pizzas do, you think?
Yes.
Okay. Next question is, do any of you have dietary requirements? I mean, do some of you
Is
not
anybody
eat
allergic to
pork
something?
and not eat something else?
Anybody like this?
I'm allergic to crust. I'm allergic to crust.
Allergic to crust? Can't have very many pieces without a crust. Sorry.
Get you a knife and just cut it off.
Okay.
Okay, plus some cheese.
Like you can't even eat this.
What's that?
There's no
5?
There's no
32. That ain't 25. That ain't 25.
I would say like.
Okay, is 4 enough?
Yes.
Okay. Okay. What kinds of pizza do you want then?
All of it.
Does anyone need only cheese? Okay. Okay, 1 cheese.
Yeah, one cheese.
One
Yeah, I
sausage.
like sausage.
It's gonna cost you extra dollars a little bit.
That's all right.
I would think you actually gonna need 5 pieces.
She said with
Calm down.
pepperoni.
If you do 2 pieces per person,
Right.
that equals out to 5 pizzas. Just
5
like
pizzas.
5.
Yeah.
Because
Okay.
there's 8 slices in the box.
Right. Okay.
What would we
So
do?
let's go with 5 pizzas then.
Alright.
1 cheese. Is that right?
Yes, one cheese. That works.
1 sausage or more?
1.
1 sausage.
1 pepperoni.
1 pepperoni.
1 Hawaiian.
that's too much.
Does Little Caesars have a Hawaiian
No.
pizza?
It's all the pepperoni or cheese.
Pepperoni.
So pepperoni, cheese, sausage. You can do
I get an anchovy
two
on it.
pepperoni.
Do one
Two
meat lover.
pepperonis?
Yeah, do one meat
Cheese and then
lover.
one sausage.
And one what?
One meat lovers.
Okay, one meat loaf.
Triple meat.
Okay, one cheese, two pepperonis,
One sausage.
one sausage, and one meatloaf. Is that gonna be good enough?
Yes.
Okay. I'll have them here at 3:15. I'm guessing y'all can have them eaten by, we'll leave some.
3:20.
I'll be here.
Oh, you'll be here. All right. Okay. So, do you figure we can start class then by what, 3:30 or 3:45?
eat while you talk.
Okay, I'm
Well,
happy
he
with
might
that.
want the pizza too.
No, that's okay. Okay. So 5 pizzas you think will be enough?
Yeah.
All right. We'll go with that, and we'll do that on Tuesday. We'll finish the chapter starting with 8.4.
They said they're gonna talk Scotty into coming here.
I bring back
Y'all for real should get Scotty to come.
Okay. Let me ask a question. Did someone borrow my pencil?
Oh no.
No.
Sorry.
Someone did. It was in another class, I think, though.
I think yelled. It's on your ear.
Yeah, that place is yelled.
And this pencil's not working.
I can give you a pen.
Uh-oh. That's a pen.
Yes, I want he's a good snow.
I don't know where that came from. We'll start with 8.4 next time. Okay? Good deal.
So, is that on my test? I'm not missing any more, am I?
I don't think so.
Okay.
Okay.
You like No.
Oh my gosh, I got chocolate on everything.
Oh, shit, I almost fell for that. I almost fell for that.
I got chocolate on this from that dessert.
Okay, that's all right. I like chocolate. Okay.
That's allowed.
Okay. All right. So Tuesday, pizza, finish the chapter, do the lab, and then anyone who wants to hang around for a test, you can do either the chapter 8 test or both the chapter 8 test and the final, up to you. I will be here all day Wednesday. I'll be here all day Thursday. I'll be on Birmingham campus on Friday. If you want to come Thursday at 3, you can come Thursday at 3. I'll be here. Okay? Now, everybody ready for the test tonight?
Yeah.
Okay. Let me shut this down.